All right, everybody, welcome to another IAEI News Live. My name is Thomas Dimitrovich. I'm recording this. This is Monday night. I should record like a few of these and just play them whenever I travel, but I can't do that because we have topics that we need to cover, and I can't just record them and just play them. So we got to keep going with the momentum. So anyway, today I want to explore, we're going to continue our discussion around these motor circuits, these things we call motor circuits. And we're going to focus on variable frequency drives. So let's talk about VFDs, motor circuits, and it all starts now. All right. I almost dropped this bolt or screw or whatever you want to call it. It's supposed to hold my camera on its mount into my water bottle. I am going to connect my iPad to the Marriott Wi-Fi and call up NFPA link, because I know everybody out there has their membership to NFPA link active, and you're going to be doing the same thing that I'm going to be doing. And for some reason it didn't come up and ask me for my room number, but let's see if I'm online. Maybe I should use my phone. I think I'm going to do that. So I remember last week, if you recall, last week we had a discussion about a process that I learned from an IEEE friend of mine. She gave me a good tip, and I passed that along to you. Treat your motor first, address the motor, get all the particulars, then select your overload protection, then select your short circuit protection, and then pick your conductor. Pick your conductor last. What a concept. You know, I think I said it on the video last week that I do that for transformers, right? I pick the transformer last, and I'm keeping my head down because I'm getting the facial recognition off of my iPad, and I am into Link. I do the conductors last because when you're dealing with a piece of equipment and when you have requirements that help you understand how to pick the protection for the equipment, you do that first. And then you pick a conductor that works. It makes sense. And in my other videos, I was going after the conductor first. And that was the Lorraine pad, and she pulled me on the side. She says, "Thomas, I love your videos." But she's a motor person, and I know she's a motor person. And if she's watching my videos, I know she's watching my motor videos. And you know, when you what I do, and you guys and gals know this, I just grab the code and I start from top to bottom. I try not to go with a predisposition. I am trying to just navigate the words in the code and read the words on the paper, and that should drive my behavior. And where my behavior and the words don't align, then something's wrong. Either, and I found locations in the code where, and I think motors is probably a good example of that. We pick conductors, we go to the 75 degree C column, and we work from there. but that's not what the words say. So, and we went through that. If you are surprised that I'm saying that, just go watch a few videos ago, and you'll see what I'm talking about. I'm a very literal person. Literal. I'm not a little person. I'm a very literal person. Anyway, now Lorraine pulled me on the side and she said, when she said that she watches my videos and she likes my videos, I know she watched the motor ones, and I was waiting for her critique. And her only advice was don't follow the code in the order that it is in the code because the conductors are up there. Focus on the motor, focus on the overload, focus on short circuit, then select your conductor. I'm like, that? I like that. I like that. It made sense to me. It was something I can wrap my head around. It was great advice. And it gave me a different perspective. So let me see if I can get this to work. It does. It works. Look at that. Kind of dark in this room. That's the bad thing about these rooms. I got a light up here that when I turn it on, it flickers like you wouldn't believe. So I can't turn that on. I've got this huge television sitting right here in front of me, the back of it, not the front. Can't even turn it on for light. I've got this light. I've got a desk lamp here. So if you wonder why it's kind of dark and dim, it is in the evening. I'm in Washington, D.C. for a NEMA meeting. And that is what it is. Now, what you'll notice here is I've got the 2026 edition, and you have it too if you have NFPA Link. And we have the 2023 edition. I am going to focus on the 2023 edition for our discussions. I'll go over and check to see if anything's changed in the 2026, but my thoughts are 2023 is going to be around for a while, especially in some of these states. So I'm going to continue speaking to the 2023 edition. We're going to focus on drives. So that's 70B. There it is right there, 2023 of the code. That little letter there is deceiving. They should change the color. I got to talk to Jeff Sargent. All right, so I'm going to go to chapter 4. We're going to go to Article 430 for motors, circuits, and controllers. Laura She Blows, Cupcake Island. Now, you know what? Let's take a look at how this is laid out. You have part 1 is general. Part 2 is motor conductors. Look at that. So that was Lorraine's point. She said, look, Tom, she goes, the way the code's laid out, it takes you straight into conductors first. And that was her beef with that. And that's the way I did my video. That's the way if you watch the earlier examples, that is exactly what I did. That's exactly what I did. I went straight to conductors first. But you should pick your conductors last. We are going to focus on drives. Oh, let's take a look at what let's take a look at what the diagram gives us. The diagram, motor overload protection, motor branch circuit conductors. Where's drives? Where's our variable frequency drives at? Why is it not in the picture? I'm a picture guy. I love this diagram. Well, let's take a look. Let's go down to, so you got part 1, part 2. Motor and branch circuit overload protection. You got motor, branch circuit, short circuit, and ground fault protection. We have motor control circuits. I would say maybe it's in there. motor controllers, maybe that's where it's at. Yeah, look at that. Because an adjustable, if you think about a variable frequency drive or an adjustable speed motors, you're basically controlling the motor. You've got a piece of equipment between you and between the overcurrent device for the branch circuit and the motor. So that says adjustable speed motors. And part 10 is adjustable speed drive systems. Why is part 10 not in the diagram? We have to add part 10 to the diagram. First, let's take a look at the adjustable speed motors. Let's see what it says about adjustable speed motors. It says, adjustable speed motors that are controlled by means of field regulation shall be equipped and connected so that they cannot be started under a weakened field. Starting under a weakened field shall be permitted where the motor is designed for such starting. Well, that's sort of... I love this. 430.88 tells you have to do it this way unless it's listed for the... I don't even know why they have 430.88 in there. It should just say adjustable speed motors shall be listed for the application. And that would cover starting under a weakened field or not. They could have put an information. I don't know. Anyway, 430.88. I'm tired. I'm tired and I'm argumentative, and that's not good. That's not a good way to start a video. You know what I'm saying? So let's go down to part 10, adjustable speed drive systems. Let's look at what does 430.120 say. Installation requirements for parts 1 through 9 are applicable unless modified or supplemented by part 10. Makes sense? Power conversion equipment used in adjustable speed drive systems have to comply with part 10 for an input or output rated 1,000 volts or lower, and with part 11 for over 1,000 volts. All right. So we know part 10 and part 11 is going to deal with medium voltage. They haven't pulled that out. Now, you know what's going on with the medium voltage stuff. They're moving things around a lot. So just keep that in mind that that if you're dealing with a medium voltage motor, it's still in Article 430. I don't believe they pulled that out in the 2026 either. It's like Transformers. Pulling some stuff out of these articles can, especially when they're interwoven. So anyway, 430.120 are your general requirements. That just sort of gives you the scope for part 10, tells you what to find here. Now, what you're going to find this is the minimum size and ampacity of the branch circuit. So this is on the supply side of the drive. And what they're showing you here is that they're telling you the circuit conductors that supply the power conversion. So this is on the line side. It has to have an ampacity not less than 125% of the rated input current to the power conversion equipment. So, again, when I see ampacity, now I know this is dealing with a conductor, and you're going to say, Tom, Lorraine told you, don't do the conductors first. I'm just going to go down through this article, this part, and I want to understand the parts and pieces. So the conductor that is going to go from the overcurrent device to the drive, you're going to multiply that by 125%. Now you're going to say, why are we doing the 125%? I know a motor can't be a continuous load. And the reason a motor, so let's talk about this. The reason a motor can't be a continuous load is because motors have inrush currents. And when you have an inrush current is not going to last for 3 hours. So when you read the definition of what a continuous load is, it's the maximum current operating for 3 hours. And the maximum current for a motor is inrush. Now on a variable frequency drive, I don't have inrush. I don't have inrush. So in my humble opinion, they could just say that the adjustable speed drive system shall be considered a continuous load. Now, I guess unless you have a bypass, if I have a bypass, then I have to consider that drive not in the picture. That's a good question. It says power conversion equipment can have multiple power ratings and corresponding input currents. So I guess you're going to have to look at the nameplate of the drive. Well, let's take a look. I'm going to continue down this road, but suffice it to say that the input conductors supplying the drive, we know are sized with an ampacity that's based on conditions of use. That means you're going to take the number of conductors in a raceway, the ambient temperature. You're going to do your D rating off of the 90 degree C column if it's 90 degree C conductors. And you're going to determine the ampacity of the conductor. That has to be at least 125%. I'm not using the 75 degree C column or the 60 degree C column or anything like that because it says ampacity. And you know where my head's at on that. I'm just reading what the words say. And if the words mean something, should mean something different, then we need to change the words. The output conductors. Now, these are the conductors that go between the power conversion, so your adjustable speed drive, and the motor. They, too, are sized at 125% or larger of the motor full load current. And in my opinion, that is, again, is that dealing with the continuous load, or is that for a different reason? I believe it's the continuous load. It says there is an exception. If the power conversion equipment is listed and marked as suitable for output motor conductor protection, the conductor between the power conversion equipment and the motor shall have an ampacity equal to or greater than the larger of the following: 125% of the motor full load current, or the ampacity of the minimum conductor size marked on the power conversion equipment. So that's telling us that you could have a variable frequency drive Sorry about that. That's telling us that you can have a variable frequency drive that provides conductor protection. And it could be marked with a minimum conductor size for that portion between the drive and the motor. So there's a couple informational notes there, but and it's pointing back to 430.6a and B or B when determining the motor full load current, because now you just have the motor, right? So you are now in the world of the motor, which we already know. We're going to use the table for some things. We're going to use the nameplate for other things. But on 431.22a, this was on the line side feeding the drive, the adjustable speed drive. Now, C has the bypass device. So, and remember, I mentioned the bypass before, and I said if you have a bypass in around the drive, that means you have a means to work on the drive. So you put it in bypass, take the drive out, do whatever it is you need to do. And it tells you the ampacity of circuit conductors supplying power conversion equipment included as part of an adjustable speed drive system that utilizes a bypass device shall be the larger of either of the following: 125% of the rated input current to the power conversion, or 125% of the motor full load current rating as determined in accordance with 430.6. And that makes sense because you have to make sure whichever one of those is larger, you want the ampacity of the conductor, because if you're in bypass mode and you're starting that motor across the line, you need to be able to handle the motor. And the drive may have a lower current rating than the motor does. So they give you that, they address that condition of when you buy and purchase and install a system that has a bypass. And then D deals with several motors or a motor and other types of loads. And it just tells you that the conductors that supply several motors or a motor and other loads that have power conversion equipment have to have an ampacity in accordance with 430.24 using the rated input current of the power conversion equipment. So go back to 430.24, which we've already talked about. Now, the overload protection. Again, so this is the interesting part of this one. Sorry about that. I clicked the wrong button, and I'm not editing that out because it's too late. So in 430.124, it talks about overload protection for the motor. It's not talking about overload protection for the drive. In some cases, the power conversion equipment is going to provide that protection for you. And then you don't have to do anything additional. When you have a bypass, you have to provide overload protection as part of that bypass. Because remember, when you're in bypass mode, you're taking the drive out of the picture for whatever reason. You're going to edit, you're going to work on it, you're going to replace it, but you're going to bypass the drive. And then they deal with the multiple motors applications. Each of those motors have to have overload protection. You're not going to have one overload protection in multiple motors. Each motor is going to have its overload protection. So 430.124 has nothing to do with the input conductors that were selected up here. Circuit conductors supplying power conversion equipment included as part of an adjustable speed drive system have to have an ampacity not less than 125% of the rated input current. So those are the conductors feeding the drive, and the overload is dealing with overload protection of the motor, not the drive itself. Then you have motor over temperature protection. This is you've got motor thermal protection. You could have RTDs installed inside the motor, things like that. You may have a device or a piece of equipment that has thermal memory. What thermal memory means, thermal memory tries to replicate the cool down of the motor. Remember, if I do multiple starts, it's going to know that you tried starting this thing multiple times. Every time you do that, you're building up heat in the motor, which changes the damage curves. There's a good session. We're going to do damage curves of motors. We did the damage curve of a transformer we need to talk a little bit about damage curves for motors. Maybe next time. But the damage curve for your motor is going to be adjusted because of the additional heat that you have built up. So you may have a drive or a starter that has thermal memory. In some cases, it could be electronic. You know, the manufacturer could replicate that electronically or digitally. Over temperature protection relay utilizing thermal sensors. That's your RTDs. What was that? Resistance thermal detectors? Can't remember, but basically the way an RTD functions is as it gets warmer, it changes the resistance. So you monitor that resistance and it tells you what the temperature is. And then you alarm on it. And you may have a motor relay that is pretty daggone complicated and takes into consideration the thermal capabilities. In fact, I remember back in the day, this goes back a long time, when I was doing system studies for Gilbert Commonwealth, there was a motor relay, a very large motor, that basically, when you had RTDs, it would adjust the protection curve accordingly. It would shift things around. It was pretty awesome. But it would monitor the temperature in the stator, and you could alarm on temperature, but what the really cool part was it would adjust the curve and provide a very good protection. In fact, it would track the starting curve. It would capture the data on a start, and then it knew the start curve for a motor. Now, you may or may not know what I'm talking about with a start curve, but whenever you have if I was going to draw a time current characteristic curve, all right, if I did so this is current, and this is time, and this is 0.01 seconds. You may have a start curve, it sort of starts off on an asymmetrical, then it comes up, and then it'll transition over. It'll transition over to full load amps. We've drawn this before. Remember, this is full load amps. This is locked rotor amps, and that's the transition, right? So that's the transition between the locked rotor and full load. So if I'm driving a load, that motor's going to work until it gets it turned. If I have like a ceiling fan, that transition is like almost instantaneous. If I'm on a conveyor belt, it's much more pronounced. If I'm on a pump, it might be much more pronounced because it may. I know I did one project where I had, in some cases, when I started the motor on the pump, there was water in the pipe that I had to push up. So it had to get things moving. But once it got things moving, and it was fine. So the locked rotor, that transition took a while, and it had to depend on the height of the. Anyway, it was a fun project. I could go on for hours on that one, but in any case, that transition from locked rotor to full load amps can vary, and then if it heats up, the temperature, your protection curves. And the one relay that we applied, I had a long time. Let's do this. Let's do it in purple. I had a long time like this. It would come over like this. It would come down. like that. And then there were these, like I called them, I, I, I called it I called them little arms, but you had trigger points where if my locked rotor, and let's say I did this, if that locked rotor passed this value, it would alarm and let me know that, hey, this is my next start might trip it, because it's taking longer to come up to speed. But your motor, your trip curve, this trip curve would dynamically move based upon a lot of different parameters, and which was pretty cool. It was slick. But I digress. But in any case, understanding the thermal capabilities, and you might have a relay. Oh, I'm sure drives do the same thing. But see, the thing with a drive will ramp it up, right? It'll change the frequency, but you have to know what you're pushing or pulling, right? You got to know what is on the shaft of that motor. You're turning, you're pulling, you're pushing something. It could be a pump. Even pumps could push or pull. But in any case, you might have thermal memory. You have a disconnecting means, and here we go. Branch circuit, short circuit, and ground fault protection for single motor circuits containing power conversion equipment. This is 430 dot. Dadgummit, I'm doing the wrong one. Me and Cam B. It is really late, and I'm really tired. So forgive me. So 430.130, branch circuit, short circuit, and ground fault protection for single motor circuits. So the first 430.130A, I would argue, is the branch circuit that's supplying the drive itself. And it tells you no, it doesn't. This isn't the drive. Because it says the rating and type protection shall be determined by 430.52C1, 3, 5, or 6 using the full load current rating of the motor load as determined. So that's no drive in the picture. So that's, and then it says where maximum branch circuit, short circuit, and ground fault are stipulated for specific device types in the manufacturer's instructions, they shall not be exceeded even if higher values are permitted. And then they talk about a self-protected combination motor controller. Self-protected motor controller, where specifically identified in the manufacturer's instructions for the power conversion equipment, or if otherwise marked on the equipment, where an instantaneous trip circuit breaker or semiconductor fuses are permitted in accordance with the drive manufacturer's instructions for use as the branch circuit, short circuit, and ground fault protected device for listed power conversion equipment, they shall be provided as an integral part of a single listed assembly incorporating both the protective device and power conversion equipment. This is not protecting the branch circuit that's supplying. I'm sorry. Here's my issue. If I think about a motor circuit, I'm going to have a panel board, right? I'm going to have a panel board. Isn't that a beautiful panel board? And I'm going to have a breaker in here feeding a drive. And on the output of the drive, I'm going to have a motor. We already know the sizing of this conductor is 125% of what's on that drive. And if I have a bypass, then I size it for that motor. But this language branch circuit, short circuit, ground fault for single motor circuits. Circuits containing power conversion equipment shall be protected by a branch circuit, short circuit, and ground fault protective device in accordance with all of the following. 1. The rating and type of the protection shall be determined 430.52C1, 3, or 5. This is that's your single phase. Oh, wait a second. This is based on the motor. It says C3C. That's C1. C1, C3, C5, or C6. The rating and type protection shall be permitted to be determined by 430.52C1 using the power conversion equipment's rated input current. Okay. So, all right. So I can, now this is making sense. I could use the exception and then go to that table using the power conversion equipment's rated input current, where the power conversion equipment is listed and marked suitable for output motor conductor protection. The motor conductor branch circuit, short circuit, and ground fault from the power conversion equipment to the motor. That's it. That's between the motor. So informational note number 1 talks about between the drive and the motor. And informational note number 2 is telling you a motor branch circuit using power conversion equipment, including equipment listed and marked suitable for output motor conductor protection, includes the input circuit to the power conversion equipment. That's about as clear as mud. I mean, why wouldn't they make it just as neat and clear as to say, look, you have a drive, you have to select that overcurrent device, and then this has to provide protection downstream. I've got to protect this conductor, and that's going to be protected by the primary overcurrent device. And I would say if I'm sizing this circuit based on 125% of the drive, let's take the bypass out of the picture, then I protect it at its ampacity. I don't have inrush currents. I don't have to worry about fault currents coming back. And then the drive gives me the protection of these conductors. So this is protected by the drive. The moment I put a bypass in, now it's a different story. But I'm telling you, this, in my humble opinion, this is as clear as mud. Circuits containing power conversion equipment shall be protected by a branch circuit, short circuit, and ground fault protective device in accordance with all of the following. Follow manufacturer's maximum branch circuit, short circuit, and ground fault protection ratings are stipulated for specific device types in the manufacturer's instructions for the power conversion equipment. They shall not be exceeded even if higher. So that's telling you, this item 2 is telling you, look, if you some of these drives will tell you what the maximum needs to be, what your protection needs to be. And then there's this self-protected combination motor controller shall only be permitted where specifically identified in the manufacturer's instructions for power conversion equipment or if otherwise marked on the equipment. What equipment? The type of protective device, its rating, and its setting are often marked on or provided with the power conversion. So they're talking about if it's marked on the power conversion equipment. And then you have the bypass. So I tell you what, I'm going to do this. I'm going to stop right there because I've got to do some more homework. I'd love your opinion on this. On that branch circuit, between the panel board and the drive, what section do you use? What section are you using in the code to protect that conductor? Are you going to 430.130? How are you handling that? Because I'm not liking the language. I don't like the language that I'm seeing in 430.130. But that's just me. All right, so variable frequency drives can be simple. Follow manufacturer's instructions. We know that the secondary is special. Fact 430.132 tells you do not put GFCIs or special purpose GFCIs between the power conversion equipment and the motor. Those aren't listed for those applications. Only put equipment in between the drive and the motor that's listed for the application. You've got to take into consideration that you could have a bypass that could be built into the system. And when that bypass is built in, you're going to need to select things based upon the motor itself and take the drive out of the picture. If you're looking at the conductor supplying a drive and you don't have a bypass, now you're looking at the drive itself. The drive will be marked. They'll tell you what overcome, and for the most part, they should, but they may not tell you what size overcurrent, maximum size overcurrent protective device, and the size, etc., for that equipment. We're going to talk more about drives. I think next time what I'm going to do is I'm going to grab some drives and we'll look at some nameplates. Maybe we'll take a look at some nameplates and we'll take a look at the standard. Before we get into thermal protection and the motor damage curves, I think we need to explore drives a little bit more. So for your homework, take a look at part 10, focus on part 10, and take a look at all the reference sections and think about that motor circuit. I've got an overcurrent device with a branch circuit feeding a drive. From the drive, there are conductors that feed a motor. What sections of the NEC apply to protect the conductors, the drive, and the motor? Pretty simple, it seems like, right? I don't know. Sometimes, just when you thought that things were simple, they get a little complicated. All right. We will talk to you next time. We're going to dig a little bit deeper into variable frequency drives, adjustable speed drives. Well, maybe we'll look at some defined terms too. All right. Thanks for joining in. I appreciate what you do for the electrical industry and what you do for electrical safety. Remember, stay safe and please stay healthy. Take care. God bless.